Hello students, today let us discuss about Foucault's experiment. So this particular experiment isn't basically a way of measuring the speed of light. Okay, speed of light is denoted by c, you know that, and we know that it is 3 into 10 to the power 8 meter per second. It is well known to us. Okay, but Foucault, basically what he did, he has calculated and he has proven the value to be equal to 3 into 10 to the power 8 in a laboratory experiment. So that is what he has done. So and it is basically the underlying principle for this particular experiment is nothing but the relation between the kinetic relation between velocity is nothing but distance by time. Okay, so it is well known to us. So c is equal to, or any, sorry, I will write it as velocity. Okay, so velocity is equal to distance divided by time. Now I'm going to draw the experimental setup for this. All other details about this experiment are written in the note provided. Now I'm going to draw the experimental setup. So for that, you see, usually we have it's a kind of mirror. Okay, so and suppose that there is a source of light. Okay, this is a laser source. Imagine like that, and this source of light is giving out like that. Okay, and ray of light is going up like this. Okay, so what I have done here, we will keep a like this. We will keep a mirror. Okay, this is a mirror. Suppose this is M1. Okay, so this is a mirror, and this is, see, I have not done any shade on it. Okay, this is a two-sided mirror. Okay, there's a two-sided mirror, and this is rotating. It can rotate. Okay, so see, it is not totally vertical like this. It is little bit inclined. It is rotating. So now what I'm going to do, suppose, let me do it as a green line. Okay, and I'm going to draw a normal on it. Fine. So this is a normal. Okay, so this is a normal, say n dash. Okay, so you know that this is the incident angle. Okay, so incident angle is nothing equal to angle of reflection. So it will, this ray will be reflected like this. Extend this mirror a little bit. Okay, so the ray is going like this. Okay, so since this mirror is going to reflect back, isn't it? So at the same time, this is a rotating mirror, right? And this is a fixed mirror. Here both sides reflected, here only one side can reflect. Okay, now suppose that when it is going now suppose that this is rotating in this direction. Okay, it is rotating like this in anti-clockwise direction. Okay, so you know that when the light travels from here to here and then going back here, there will be a time gap. So within that time, what will happen, this mirror is going to change its position slightly. Okay, so let us write down that the omega is a angular velocity of rotation of the mirror. What is the name of the mirror? M1. Okay, this is say M2. Fine. Now Now the mirror has come to a new position, isn't it? So this, let me name it as M1 dash. Okay. Now suppose that the angle between them, I can extend it, isn't it, to show you the angle. So angle between them is equal to delta. Okay. So again I'm repeating, see, this is a laser source. Okay, it's a laser source. The ray of light is coming like this. This is the beam splitter. Fine. What beam splitter will do, this is the ray of light initially starting from here. A part will go in this direction and another part will come down like this. Okay, and there is a fluorescent plate here, so it will note down whenever the light falls on it. Here there will be a spot created. Okay, so that spot is noted. Now the ray of light is going like this, like this, like this, and you can see this blue one. Okay, the blue one is a mirror. Okay, both sided mirror that we were talking about. And this blue is the normal to the mirror. This initial position of the rotating mirror, you can see that. Okay, now when the ray of light is falling, this is an incident ray of light, just mind it. So this will be the what, this is the angle of incidence. Okay, so it will make the same angle of reflection, so this is an angle of reflection, so it is a normal. Okay, drawn at the point of incidence. You know that angle of incidence is equal to angle of reflection, so it will go like this, and there is a fixed mirror and it is one-sided. So what will happen, the ray of light will bounce back. And now when this coming back, and then what will happen, this blue rotating mirror, this is a blue position, so within that time what will happen, it will not be there, it will change its position because it is moving in the anti-clockwise direction. Okay, so it is coming to this position. So let me name it, this is red color. That new position I am showing by red color. Now on this new position of the mirror, I am drawing another normal. You see, red normal. Okay, because as the mirror is changing, the normal will also change, isn't it? Now you see, this time when the ray is coming and reaching the mirror, this time the normal has changed, so angle of incidence has also changed. Mind it, this one is angle of incidence, new angle of incidence. Okay, now it will make, so angle of incidence is again equal to angle of reflection. So it will, the ray is falling like this, considering red to be the normal, it will reflect back like this. Okay, so this is the new angle of reflection. Are you getting? So this is a new angle of reflection. It is coming back and back, but this time you see the path has changed. If the mirror is not rotating, then it will follow the same path and come back like this. But since the mirror is rotating this time with an angular velocity omega, so what will happen, now it has followed a new path and it is coming like this, and it has made the beam splitter, and it will, a part of it will reflect like this down towards the fluorescent plate. So this distance, so what we do in the spectrometer or telescope, the spectrometer, what we'll do, we will observe this fluorescent plate and we will see the difference between the spots. Okay, so this one is considered to be del x. Now you look at the geometry. That's very careful. Be very careful. Now you see, let us consider that within suppose there is a time t. Okay, within the time t, with the angular velocity, the this particular thing is rotating, so it has rotated through an angle del theta. Okay, del theta. So you see, now you need to look at the now you know that this is, if this is del theta, angle between the mirror is del theta, rotating position of the mirror is del theta, then angle between their normals will also be del theta, isn't it? Because they are perpendiculars. So there is a theory on geometry that if two planes are there, the angle between them is theta, then angle between the normal drawn on them will also be theta. So like that. So normals are red and blue. So initial is blue, then red. So their angle between them will also be what? Del theta. I hope you don't have any doubt on that. Now what we need to do? This is the initial part of the ray of light. It was supposed to come back in this direction, but it didn't come back. It came back this direction, is it? So we need we need to find out the angle between this. So let me turn it as red. Okay, we need to find what is the angle. Okay, what is the angle between these two, initial ray of light and new ray of light, or deviated ray of light. We need to find this angle. This is a question mark for us. So to find this angle between the initial ray of light and deviated ray of light, now let's go to this position. You can see that. Let's find out. So this is, can we consider like this one plus this one? So for this, you see, this is nothing but the whole thing is what? Del theta. And this thing is nothing but I, isn't it? This thing is I, whole thing is del theta, this thing is I. So this thing will be what? Del theta minus I. I will so send you the picture of this particular sketch. Don't worry about that. And then similarly, see, this is the angle of incidence. So this is angle of reflection. Okay. Now you see, this is del theta. This is I. The whole thing will be del theta plus I. Okay. That thing. So angle of incidence is equal to angle of reflection. So this will also be del theta plus I. Okay. So this whole angle is nothing but this much plus this much. This much is del theta plus I. This much is del theta minus I. So the total will be what? Del theta plus I, del theta minus I. So it is twice del theta. Alright. Now let us look into the derivation. Okay. What was done here? So let us consider that the distance between the fixed mirror and the rotating mirror is given by d. Okay. So what we have now? We have t, time t. Okay, we will have to check within the time interval between which the initial ray of light and next ray of light is coming, because when the mirror keeps rotating, you will keep on receiving another rays of light also. So first of all, you need to find out first time gap, that is t, angular velocity omega, and gap angular distance is del theta. Okay, so for that, now consider that, can you see this triangle? It's not looking right angle triangle, isn't it? It's not looking at all like a right angle triangle. But what we're going to do, we will imagine, we approximate. Okay, this is just an approximation. This is an approximation that this is kind of right angle triangle. Because you see, I'm not considering this in a 3D. Okay, if you consider this in 3D, this will be normal. This thing will be normal. Okay, we are not considering, we can't do that in 3D, imagine like that. So approximately this thing will be normal. So it is looking like a right angle triangle. So if I consider this to be a right angle triangle, this to be 90 degree. So this angle to be twice del theta, this angle is twice del theta. So 10, sorry, let me write it like this. 10 twice del theta is equal to nothing but perpendicular over base. As I already told that 10 theta is equal to perpendicular base. So here theta is nothing but twice del theta, is it? Twice del theta. So 10 twice del theta equal to perpendicular by base. I told you that although this thing, the whole triangle doesn't look like a right angle triangle, but since if you imagine in 3 dimension, then it will be approximately a right angle. Okay, so this is 90 degrees, so this is the angle, isn't it? So this will be the base. So base is approximately equal to r. Remember that these are all approximate. Okay, these are all approximate. Okay, because this experiment, see, this experiment is done is very minute scale. It's not a big scale. It is just because we are dealing with light. It deals in, it's a very means even in millimeter is not enough. It is very tiny scale. So in that scale, definitely this angle is going to be 90 degrees. So this is approximately r. Okay, and this is the perpendicular, isn't it? This is hypotenuse. So this is the perpendicular. So for that, what I need to do, I will have to find this thing, how much it is. So experimentally it is said that, you might be finding it very weird, but it's true. Experimentally it is thought that this thing is approximately equal to this, because you see my diagram is not good. Okay, I'm not able to draw the precise diagram, because you see, if you in case of light, what will happen, this two rays, you can see so much of big gap is there. Usually it will not happen like that. The gap will be very tiny like this. It will come back, and it will go and come back like this. You won't even imagine. Okay, so it is so close to each other. This del theta twice del. See, del theta, we are not writing theta, we are writing twice del theta, means it's a very tiny value. So under the situation, this thing will be approximately equal to this thing, and this thing will be approximately equal to this thing, means del x. Okay, just imagine with tiny measurements, this thing is equal to this thing, and this thing will be equal to this thing approximately. So that's why base is considered to be equal to approximately equal to del x, the distance between the two spots, initial and final. Fine. So del theta is equal to del x by twice r, that you consider. Now t will be time taken. So you see, the ray of light comes from here to here and then goes back. Okay, this is the distance. So if one time is d, so return will be twice d. So this whole thing happens within a time frame of t. Okay, t seconds. So this total distance covered is how much? Twice d, and velocity is c. So you know that c equal to distance means velocity equal to distance by time. So here it is c equal to twice d by t. So t will be what? Twice d by c. All right. So that's done. This is done. Okay. So this one is also done. We have understood. So now let us talk about the what I can say, angular frequency of the mirror. Okay, so the mirror is rotating. Angular frequency means in 1 second how many times it is, how many rotations it has done. Okay, so omega mirror is again similar thing, distance by time. If you write in angular format, angular velocity, angular distance divided by time. So angular distance is nothing but what? Angular distance is del t in time t. So omega mirror is equal to, in place of del theta, del x by twice r, so that I have put from here. Okay, all right. So del x by twice r t. So t I can write as del x by twice r. This will bring here. This will be so cross multiplication. So twice r omega mirror. Okay. So t is nothing but, again, t is nothing but twice d by c. So I am putting del x equal to twice r omega mirror. Okay, so I need, what is our aim of doing this experiment? We want to know the velocity of light. Okay, so c is equal to, it will be again cross multiplied, 2 into 2, 4 r d omega mirror divided by x. Again, you know that omega, angular velocity, is equal to twice by nu, frequency. Okay, so in place of omega mirror, what I will write? Omega mirror equal to frequency mirror. So twice, if you put a twice by, it will be 8 pi and f mirror. So it is equal to, so c equal to this one. Okay, I will talk about it later. Now you see, now let us talk about frequency of a mirror. Okay, so there's a problem. You know, this mirror is, I told you, both sided, means it can reflect from both the sides. Okay, so what will happen in a particular time t, how many rotations it has done? Okay, how many rotations it has done during that time? Suppose, since it is reflecting from both the sides, you will always receive double the reading. Okay, suppose there is only one light has to come back, but you will receive two lights because it is double sided. Okay, you will receive double the amount. If actually if you are getting some one data, it will be twice that data. Okay, so for that we need to modify that thing. So what is that modification? Frequency of the mirror will be equal to, so we will have to make half of f measured. Okay, that means what I want to say, that whatever you are measuring is always twice the actual value, because the mirror is twice. So you will receive two ray of light for one ray of light, because it will reflect from both the sides. See, we got this much. So what I'm going to do, 4 r d omega mirror means twice pi F mirror. So this is the actual frequency of the mirror. Fine. So it is del x. So it will become 4 to the 8 pi r d F mirror by del x, isn't it? So that's what. But here this F mirror means actual frequency of the mirror. But we are doing an experiment, isn't it? We are doing an experiment, so we will get experimental value, isn't it? So as I told you that this mirror is both sided. So if actually one light is coming back to you, but actually we will receive two lights. So that means whatever you are measuring, F measured is always twice the actual frequency of the mirror. Okay, so you will always receive double because it is double sided. Mirror is double sided. So F mirror will be equal to half of F measured. Fine. So here we will just put it F mirror. We will put a half. So half means 8 divided by 2. Again it will be 4 pi RD. Now this time is F measured means experimental. Fine, divided by x. Okay, so this is the final formula. Because we need F measured, we need experimental, because we are doing a lab experiment. Okay, so we can't actual frequency of the mirror is F mirror, but we are doing experiment, so we will get only F measured. But for correction, what I have done, that we have multiplied it by F mirror is equal to half into F measured, that we have modified, and this is a final formula for the speed of light calculated in the lab. Okay, this is and they just wanted to prove whether it is exactly equal to 3 into 10 to the power 8 or not. Okay, so for that what you need to calculate, we need to calculate the del x, distance between the two spots on the fluorescent plate. You need to know d, you need to know r, means distance between the beam splitter and the rotating mirror. Okay, that's all. If you and F measured, you will have to do it from a particular sophisticated instrument that which can calculate the frequency of the particular mirror which is rotating. So if you put all the values, you can calculate the value of C, that is the speed of light in vacuum, in an experimental setup. That's all about Foucault's experiment.